All right. Thank you for introduction, and thanks the organizers for letting me speak again. It's been a real pleasure to be here in Cambridge for in the whole program. So I will actually continue on what Mark was saying this morning. I will expand on it and show a little bit how, by using optics essentially, one can determine some important properties of the light-sensitive elastomers. So I will not talk much about elastomers themselves because this has already been explained a lot. I will show mostly continue a little bit on this process of nonlinear absorption and bleaching in photosensitive elastomers and actually any other highly absorbing system. This sort of phenomenon of bleaching is a very important phenomenon in all area of optics and spectroscopy, and it's used in many different contexts, from laser physics to microscopic imaging and similar things. Then I will show that by doing recording a patterned light in the system, that means essentially holography in photosensitive elastomers. So when we write diffraction grating, which we then probe by a probe beam, we can determine several important parameters that are difficult to obtain by usual spectroscopic techniques. And then I will also explain this or show these parameters. I will also go through some basic elements of the diffraction theory, that is important both in writing a diffraction pattern and in reading it out. So essentially, this is elements of holography. So we all know, I mean, this has been shown now several times. So when we have a sheet of liquid crystal elastomer doped with azobenzene or any similar material, due to the decrease of the order parameter, it shrinks under light illumination or UV light illumination. And if this shrinkage is inhomogeneous, which it will be necessarily due to inhomogeneous profile of light and cis isomer concentration through the sample, it will change shape. In simple examples, it will bend, but other changes in shape are possible, as we have seen right now. So in all these systems, even at relatively low concentrations, at the concentrations of a few percent or less of azobenzene. Azobenzene is a very strongly absorbing substance, so the absorption length is very small, of the order of microns. So if you want to irradiate into depths which are larger than a few microns, then you necessarily must rely upon this nonlinear bleaching process. So let me then go a little bit. So this for mechanical effects, both light and spatial distribution of the cis isomer is very important. And as I said, the absorption coefficient is rather large, so that means that the bare length is of the order of microns. Now the problem has been treated actually to quite some large extent in the papers of Courbet and in Mark Warner and Van Osten in 2009. But we will see that in the case of homogeneous illumination, it is actually very difficult to get the basic parameters like the absorption length, just due to this complication of the nonlinear processes. So I will show that Bragg diffraction holography can help out with this. Now let's go back to these basic, seemingly rather simple equations for the plane wave light propagation in the sample. So we have the light is being absorbed, And there are two contributions to the absorption, and I will show that this is very important. Not only do we have absorption of the main trans component, which is much more strongly absorbing at the wavelength, let's say 360 or something like that nanometers, but at the absorption, there is also some residual absorption, even though we are off the peak absorption for the cis component of the cis conformer, and that will turn out to be important. So I have written absorption coefficient in this way. This is scattering cross-section times the concentration of the particular species. Then we have also, I have exchanged in some, sorry, this goes up and this goes down, doesn't obvious. So then we have also local change of the concentration of the trans conformer, and due to the light absorption, and this eta here is the quantum efficiency once you excite azobenzene molecule to the electronic excited state. It can go either back to the trans conformation, or it can switch to the cis conformation. Actually, this quantum efficiency for going to either conformation is of the order of 20% of going from the excited state to the cis conformation. So many photons are actually wasted. 80% of the photons are wasted on heating. Only 20% are used for the trans to cis process. And then we have also the light-driven back process going from the cis conformation back to the trans, again with some different, of course, cross-section, much smaller cross-section, and a somewhat different, possibly different quantum efficiency. And then, of course, then we have the thermal back relaxation of the cis component. Now, this thermal back relaxation at room temperature turns out to be in this usual, the most usual azobenzene derivatives that are being used, rather long. But it's, of course, since it's thermally activated, it shortens as you increase the temperature, and let's say the transition temperature of our material at around 80 degrees Celsius, this goes to somewhat less than minutes, so much considerably shorter than. And as I say, I will show that this process of cis absorption and back reaction is very important. Now, this is one measurement of the cis. We have actually seen the same picture just a little while ago. The absorbance of a sample that this is a trans absorbance, and this is supposedly cis absorbance, but I must warn you that it is the cis absorbance, the actual cis absorbance is probably linear one is probably much lower than in this measurement. This measurement was obtained by the authors after long illumination at the peak of the trans absorbance. But even after very long times, you could not count, due to just these nonlinear processes, to have only cis components. So this is both, really. The actual cis absorbance is smaller, but it's still considerable. We will actually get the number. It's probably worthwhile looking a little bit how this molecular process, this kinetics of the molecular kinetics of the process going from trans to cis looks like. This is a computation by Claudio Zanoni and his people, and so they have actually considered not the main optical transition at 350 nanometers, but a weaker one at somewhat longer wavelength. So actually, which goes to the closest electron excited. But this is not seen very well. So anyway, so it first goes from the ground state in a trans electronic ground state to the first excited. It still does not enough contrast, seemingly. And then this surface is the surface of in terms of two vibrational degrees of freedom, which are important in this particular case. And obviously, there is a minimum in the excited state, which is different from the minimum of this vibronic band in the trance state, and it actually touches the maximum of this vibronic elementary ground state at some point. So when the system by vibrations transits to the minimum of the excited electronic state, it can go to either cis or to trance. And of course, the reversed process is similar. So now there are the equations. If you neglect the two equations that I've shown before, if you neglect both the thermal back absorption and the optical back reaction, you can actually get a very simple analytic solution to the equation, which is essentially just a Fermi function that monotonously progresses into the sample, and this time variable turns out to be very simple expressed. It's just this combination of the quantum efficiency times scattering cross-section times the light intensity in terms of photons per second per square centimeter. Now, so this is how it looks like. So it's a very simple step function progressing into the material, like you'd expect. And the velocity of this is a very simple expression. It's just the quantum efficiency times the photon flux divided by the concentration of the azobenzene. And if you calculate this, this is essentially saying how much photons are used for converting the material. And if you calculate this with the usual parameters, you get that this velocity of thickening of the cis component is something like, let's say, a fraction up to maybe a micron per second. That means that a usual sample of something like 100 microns should get transformed in something like 100 seconds. The actual times that are being used to get saturation in all these systems is most often much, much larger. So this is one of the things that has to be explained. Why do we need more time than this, what we calculate from this simple counting of photons, essentially, to get to the saturation?
What's the quantum efficiency in this calculation?
It's about 20%, as I said. Yeah. I mean, the quantum efficiency is known essentially from spectroscopic measurements of azobenzene in low molecular weight solvents. So now, if one does integration of full equations with, then, as already Mark said, you cannot get an analytic solution for the time development of the distribution of either light intensity or of the concentration of either cis or trans component. But this is what you get. It's if you neglect the back absorption, the cis absorption, then first of all, you see that the depth to which you progress at infinite time is considerably larger. And I will actually show some estimates how much larger. And also, if you really look at this, how this front goes, it doesn't go linearly. It goes essentially logarithmically with time until you get close to the saturation limit, which is much smaller if you include also the back reaction, photo back reaction. And it's actually, one can get an estimate, or actually in the case of neglecting, well, one can get an estimate for the velocity of the front when you include both the back absorption and the thermal relaxation. for small enough, for large enough intensity, and when we are not, let's look back at points somewhere like here, where we are not close to the end of this saturation process. At this point, the concentration of the cis or trans component is stationary, so we can use the stationary solution for the rate equation for the this, then put it back into the so then this is approximately, as we see, constant. So we can in that part we can say that the intensity is nearly exponentially decaying by some absorption coefficient, which is just about twice the absorption coefficient of the cis component. So then we can use this simple rate calculation, how the front progresses, and we see that you get a differential equation which one can solve, and we see that the maximum depth to which we get at a given time logarithmically increases with time and with the input intensity. Not linearly, but logarithmically. Of course, for short times, this is linear. For long times, it becomes logarithmic, and then, of course, at the end, it saturates. But we can also get the maximum depth to which we can get at infinite time. We have no cis. We can get an analytic solution to that from the solution that Mark already showed, where we have essentially linear decrease of the intensity all the way nearly to the end, and we can plug that back into the stationary equation for the concentration, and this is what we get then. So it's essentially linear function of the intensity, and of course it depends on the relaxation time. The longer the relaxation time, the deeper into the sample you can progress. Some logarithmic correction, which is important. But when we include the cis absorption, then it is still possible to get an analytic solution, but it's ugly. But the main contribution looks like this. So in that case, the maximum depth to which we can reach is only a logarithmic function of the intensity and this thermal relaxation time. So this explains why we have so much thinner layer as in saturation with the back absorption. So back absorption, even when it's very small, makes a big difference, a qualitative difference. All right, so now we have seen that when all these elements are being put together, this numerically calculated distribution is put into the elastic problem. The curves of stress versus illumination time are perfectly fit when you fit one curve and just take the known thermal relaxation time at different temperatures. All the curves are fit by the same set of spectroscopic parameters. And one thing that comes out of this fit is, for example, that the cross-section for cis absorption is about 2% of the cross-section for the trans absorption. We also get different quantum efficiencies, approximately a factor of 3, but this is not very reliable. But this is quite sort of robust in this fit. So obviously, it's very important to know the thickness of how much of your material is being transformed from trans to cis. But it's difficult to obtain that by looking simply at the light transmittance data, because this is very often you will not get anything through. If you get something through, it's going to be rather small, so there is lots of noise. And then you have to analyze that either as a function of time or as a function of thickness. So this is it's not very easy. And so we can use for that holography, as I said. And the other interesting point to make is that by using holographically patterned light, one can induce more complex shape changes in your photosensitive material. So let me explain a little bit how that works. Let's say the simplest situation, and a practically rather important one, is you take two laser beams, two coherent beams, you cross them in your sample, you will get modulation of the light intensity, which is depends on the wavelength of light and on the crossing angle. The larger the crossing angle, the finer the modulation. Now, since if we have this photosensitive material, in the dark areas, the material will stay with high order, high nematic order. In the illuminated areas, the order will be smaller. And this, of course, produces, through the dependence of the index of refraction on the nematic order parameter, rather large, relatively large, up to 20.2 or point something like that, modulation of the indices of refraction, both indices of refraction, ordinary and extraordinary. Extraordinary produces somewhat larger modulation. Now, I have to remark here that, of course, all these phenomena are also strongly polarization dependent. I will not talk about it, but let me just remark that the absorption of azobenzene is strongest when it's in the trans configuration, when the light is polarized along the axis of azobenzene. So this is, of course, something that can also be exploited quite profitably, especially, let's say, in polydomain elastomers, where by choosing polarization, you can choose which domains do you excite, and therefore choose in which direction the sample will, for example, bend. But I'm neglecting, and also diffraction properties of the resulting grating depend, of course, on the polarization, and that can be exploited too. But since this is quite complicated, I will not look at it now. Now, as I said, this holographic pattern recording can also be interesting for optical applications, because we can get large index modulation in a semi-solid material. So this can be again exploited. For example, if you stretch the material, you change and this works like a diffraction grating. So you change the wavelength of maximum diffraction and things like that. Now, let me explain a little bit more how this diffraction problem. So we can look at the gratings by using some probe beam, let's say a helium neon beam, which we hope will not disrupt if the density is low enough, the concentration of the azobenzene, of the trans or cis component. And there is a special scattering geometry which is called Bragg scattering, and it has these properties. You need for Bragg scattering, of course, you get diffraction on a periodic structure at any, if the structure is thin enough, at any incident angle. But there is a special incident angle which is such that both the incoming beam and the diffracted beam will form the same angle with respect to the, let's say, this perpendicular direction. Then we are in so-called Bragg condition, which I will explain a little bit more in detail immediately. Now you can do what the people in X-ray business call rocking curve. So you just turn the sample with the same light direction and look at how the scattering intensity varies. It turns out that in any case, you will get maximum diffraction intensity when this Bragg angle condition is fulfilled. And not only that, the angular width of this Bragg diffraction pattern is just inversely proportional to the depth, to the thickness of the grating, in other words, to the depth to which the sample has been transformed by the writing light. So let me explain a little bit how this comes about, because this is a very general sort of problem in optics and can be explained in a few steps. So the way you usually, and this is also the approach that can be used in case of, let's say, analyzing light propagation in photonic crystals. So we have wave equation, now it's written in scalar wave, so this is a big simplification really, where the index of refraction or the dielectric function is periodically modulated in one direction, and I also allow in this particular case, since we will need that, it has also some dependence into the depth of the sample. Now, the way how to analyze this is you can decompose the electric field into Fourier components parallel to the sample direction, so it means to the modulation direction. And of course, these amplitudes have some z dependence, undependence into the thickness of the sample, times some plane wave phase function. Now you plug that into the wave equation, and you arrive at a recurrence relation for the amplitudes. Now we are only interested in the first diffracted wave, so by first using this relation between the wave vector components and the magnitude, so essentially the frequency of the light, the magnitude of the wave vector, one can get this rather simple looking equation with this parameter beta being the modulation wave number of the divided by this z component of the light wave number times this perpendicular wave number minus plus the modulation number. So then let's look a little bit closer how this solution looks like. So the solution of this differential equation, this simple one, is simply can be written like this. This is a simple phase factor times some amplitude, which depends. I forgot delta F's. Oh no, it's in here. Okay. Times an integral like this, and this is nothing but z Fourier transform of the dependence of the modulation of the index of refraction. Actually, all this is nothing but a very general statement that in single scattering approximation, the scattered amplitude is a Fourier transform of the structure on which you're scattering. It's just a special case. Now, of course, if in the simple case, when the modulation is a constant in the z direction, you get this sine x over x square function for the diffracted intensity, where the width of the diffraction peak is going to be determined by the thickness of the sample. But if we have a decaying, let's say an exponentially decaying, in simple case, modulation into the sample, then the diffracted amplitude will look something like a Lorentz function, which is going to be largest in all cases when beta is 0, and beta 0 means that the transverse component of the must be related in this way to the modulation wave number. This is nothing but the Bragg condition. And around the Bragg peak, around beta being 0, the width is simply given by the depth by the thickness of the inverse thickness of the grating. So the prescription is you get the diffraction intensity, diffraction pattern, look at the width of the Bragg peak, do Fourier transform. The width of the Fourier transform will give you the depth of the diffraction of your diffraction grating. Now there is another optical problem which has to be addressed, and this is the writing problem, which is actually quite similar, but since we cannot use the same procedure here, because at every point we have to worry what is happening to to the concentration of the azobenzene. So we have to again use another technique of optics. Again, we start with the wave equation for the light propagation into the sample. But now, again, we write it in a form which is a plane wave times some modulated function. And this is going to be, again, a periodically modulated function with some amplitude. And we assume, of course, that this amplitude, which is still a function of x and z, is slowly varying in z. Then we put that into the wave equation, and we get something which is called a paraxial wave equation, which looks essentially like a Schrödinger equation if you look closely. Now, which contains a sort of a potential, the modulated part of the index of refraction. Now, there is both a real part of the index of refraction, which is modulated, but it turns out that in our case, when writing diffraction grating in azobenzene, this is nearly negligible. So I have only input here the imaginary part, the absorbing part of the dielectric function, which comes from the absorption of light on azobenzene. And by comparing this expression with the usual expression for the exponential attenuation of intensity, you can easily convince yourself that this imaginary part of the dielectric function can be expressed in terms of the absorption coefficients divided essentially by the vacuum wave number. And then we have also the same equation as before. So this is the now light equation describing the absorption process. And this is the same equation as before describing the population of the cis and trans components. Now, must be solved numerically, of course, and this can be really solved by the same technique as say what single dimensional wave equation. Okay, will that go away or not? It's Skype. Okay. We simply discretize on a mesh, and it's quite easy to solve numerically. And then you also locally iterate this with a given optical field. One iterates this population equation. Then we can get the distribution of the trans or cis component in the system. Now, this upper line shows what one gets when one uses this very simple Fermi function approximation and takes a time space-dependent initial intensity. For short times, for short illumination times, this is fine. But for long illumination time, we obviously get a very wrong form of the cis distribution or trans distribution. First of all, the depth of propagation is much larger, as I have already shown, but also the form is wrong. This is partly due to not including the relaxation of the cis component, but it's also due to not properly including the diffraction of the writing light, because the light both diffracts and is being absorbed in the medium. So now the next step, of course, has to be so this is the transverse section of one of the saturated part of this concentration profile, and we see this is far from being a sinusoidal function. It's a highly peaked function, so the first Fourier component is actually not very large. It's smaller than you'd expect. So, and this is how the first Fourier transform now of the index of refraction modulation will look like, assuming that it is proportional to the concentration. Now I will show that this assumption can break down in a very important. So then we can calculate how the Bragg peak looks like, and obviously, this is now the model calculation. We see that it gets broader and broader for longer illumination, narrower and narrower for longer illumination time. And from here, we could get back the thickness to which it is absorbed. So now the experiment looks like you'd expect. And from fitting to the peak widths, we can get how the depth of the grating progresses with time. And we see that it really goes, this is logarithmic scale, so after initial time, it really goes logarithmically, like I have explained before. And from comparison with the experiment, from this fit to the experiment, we can actually get the values of the parameters. We can first get the linear absorption length, the bare absorption coefficient, which agrees quite well with the values published for low molecular mole weight solvents. We can get the ratio of the cis to trans absorption coefficient, which in our case is about 7%. Get this intensity, which is 1.4 seconds. Now, this parameter depends also, besides the cross-section, on the quantum efficiency. And it is known that in low molecular weight solvents, this quantum efficiency is about 20%. Now, we can calculate from our data that we get for the quantum efficiency something like 0.14. I don't say this is very reliable, but it is certainly not very different from that. And this is in a way surprising, because if you think about it, this quantum efficiency was obtained in low molecular weight solvents, so when the azobenzene molecule is quite free to move. Now, in a medium like elastomer, you have both the polymer chains and the nematic order, which is certainly constraining the movement of the azobenzene as it undergoes isomerization, but still obviously not all that much, because this quantum efficiency is not much smaller than in low molecular weight solids. I guess I have to finish here. Thank you. I have.
Do we have questions? Yes.
Nice presentation. Thank you very much. You compared your numerical results with the experimental results.
Yes.
For X-ray, for diffraction pattern.
Yes.
The diffraction pattern, what you showed us as experimental results, was UV diffraction pattern or X-ray?
No, this was a helium-neon probe beam, but it doesn't matter. You just have to use a probe beam which does not cause either trans to cis or cis to trans conversion.
How you did it experiment? Do you have device for that?
It's helium-neon laser.
Oh.
It's a low intensity helium-neon laser, 0.5 milliwatts.
Okay. At the modulation, in your formula, you mean this is the constructive interference or the...
In writing?
Yes.
Yes, of course.
Thank you.
Essentially, two-beam interference. In optics, has different names like four-wave beam coupling, two-wave beam coupling, whatever. It's essentially hologram writing. This is the same principle applied, the same principles optical applied to the general writing of holograms and reading them.
Thank you for a nice lecture. I have a question. I don't understand your system you use. Is it elastomer swollen in some solvent or?
No. It's just simple elastomer doped with 10% in our case.
And you assume some phase transition with the trans-cis isomerization?
I have this problem at the continuation of this lecture, but I didn't get that far. Yes, we can actually also measure, when we go close to the phase transition, we can exploit the nonlinear relation between the changes of the order, pneumatic order parameter and
Refractive
and
index.
cis concentration, the way Mark Warner has explained, to get the sensitivity of the pneumatic order on the cis concentration. It turns out that with 10% of cis, you decrease the transition temperature by something like 50 degrees or something like that. So essentially, 10% of cis component is enough to kill your pneumatic order.
Okay, thanks.
You gave the ratio of the trans-cis cross sections. How orientation dependent is that?
I don't know, but it must be, because obviously the cis component, the dipole moment of the cis component does not have the same orientation as the trans. Since we were using for the illumination, we were using unpolarized light. It doesn't really matter here. This is some angular average of the absorption coefficients in this case. But it would be, I mean, it would be helpful, yes, and interesting to look at polarization dependence. We haven't done that yet.
Okay, I hope that this discussion can be continued during the coffee break. I would like to make an announcement that this Saturday in the evening we'll have punting